In this video, I'll introduce conditional random fields. I'll talk about how they fit in among the other classification models we've talked about, and then provide some intuition behind their design. After that, I'll walk through the equations that they use for classification and parameter training. So far, we've learned about a variety of different classification techniques. We started out by learning about HMMs, which were an extension of finite state automata. Then we moved on to naive Bayes, and then in this module, we've focused on logistic regression. Conditional random fields are another common classification technique in natural language processing. When you're categorizing different types of classification techniques, there are several important distinctions that can be made between approaches. For example, there's the type of label they're designed to provide. So naive Bayes and logistic regression were built to provide a single label for a cohesive text instance, whereas HMMs and CRFs were built to provide sequences of labels. There's also the way that the model works behind the scenes. Naive Bayes and HMMs are generative models, whereas logistic regression and CRFs are discriminative models. In fact, conditional random fields are in a way just a generalized multi-class version of logistic regression, and I provided some links to reading material in the course material that will explain this relationship further if you're interested. CRFs offer increased flexibility relative to HMMs for sequence labeling, because rather than modeling joint probabilities over observations and corresponding labels, they model conditional probabilities over label sequences given specific sequences of observations. This allows them to more easily capture long-range dependencies and helps them avoid making inaccurate independence assumptions. Conditional random fields are a special case of Markov random fields, which are undirected graphical models that satisfy the Markov property. Basically, the probability distribution for a set of variables depends on functions computed over fully connected subgraphs. These functions are called potential functions, and with CRFs, they're based on transition and state-based feature functions. So a potential function could not be computed over the nodes in this subgraph because y sub 2 isn't connected to y sub n minus 1 or y sub n. However, it could be computed over the nodes in this subgraph since it's fully connected. In graph theory, this is usually referred to as a maximal clique, or some people pronounce it clique. So going back to conditional random fields then, a CRF seeks to compute the probability of a label sequence. So we'll represent that as y here, given an observation sequence, x, and then the model parameters. It does so by taking the normalized product of a bunch of feature functions, which check for characteristics of observations and or states at different points in the sequence. To train the parameters of a CRF, you can minimize the cross-entropy loss, just like we saw with logistic regression. The log likelihood for the CRF equation we just saw is here. We would need to take the derivative of that in order to find the gradient, so I have conveniently provided that derivative here. You end up needing to find the expectations of your different feature functions. When computing the expectation, there are way too many possible label sequences to do this naively. We just don't have the time to go through every possible label sequence. So this takes us back to an old favorite that we saw with HMMs, dynamic programming. Basically, you end up with an equation that looks a lot like the forward-backward algorithm, where alpha has your forward probabilities, beta has your backward probabilities, and then m computes matrices based on feature functions. If you're interested in reading a lot more in depth about CRFs, I've provided some links to some useful resources in the course materials. Overall, we saw that CRFs fit in nicely with the other classification models we've seen in this course so far, and they're a useful discriminative model for predicting sequences of labels.